All right, now let's talk about probabilities, but we'll get a little bit more sophisticated with them. We can talk about discrete random variables and continuous random variables. When we have discrete random variables, then we'll talk about computing probabilities via summations. If we have continuous random variables, well, essentially what that means is that their behavior is governed by some continuous density function, okay? And then to find the probability, it's going to be some area beneath that curve, okay? If you've taken a basic statistics course, this should not surprise you because you can think about what you did when you evaluated probabilities for normal random variables. They're actually exactly areas beneath the normal density curve. Okay. All right, but let's start with a discrete example. Suppose that I have a random variable big X, and big X will denote, say, something simple like the number of heads you get in 2 coin tosses. Okay. What are the possible? How many heads can you see in 2 coin tosses? Well, you can see 1 head, you can see no heads, or you can see 2 heads, right? Yeah, I think that's it. 0 heads, or 1 head, or 2 heads. Okay. What's the chance that you see no heads? There's 1 way out of 4, right? What's the chance that you see exactly 1 head? Well, that would be, let's see, if the first one's heads and the other one's tails, or the first one's tails and the second one's heads, right? So it's actually 2 out of 4. What's the chance that both are heads? It's 1/4, okay? And that's all the possibilities. Now, what if I'm interested in the chance that x takes on a value between, say, 0 and 1? It's pretty easy, right? This says to sum up, okay, goes from 0 up to 1. Right, that's what my instructions say. From 0 up to 1, the probability that x equals k. Well, so in this case, that's just going to be the probability that x equals 0 plus the probability that x equals 1. Okay, pretty easy, right? That's just so that's 1/4 plus 2/4, 3/4. See how simple that is? Yeah. Okay. What about, on the other hand, if x is continuous? Suppose that suppose x has an exponential lambda distribution, meaning that the density function for it, and I'm just going to indicate that we're talking about the density function for x by putting the name of the random variable down here in the subscript. This is just a tag. It's a label. Okay. This thing looks like this. It's lambda e to the negative lambda x for x greater than or equal to 0 and 0 otherwise. Okay. And we saw from one of our previous examples on page 13 of these notes that the density function then actually looks like this, right? Looks like this. It's a very special density function, by the way. This is lambda. Lambda can be anything you want. Okay, sometimes it's 1, sometimes it's 10, sometimes it's 110.2. All right, it's just a parameter of the distribution. Okay, here's my x-axis, and so in this case, maybe we want to know the probability that what's the probability that x takes on, say, a value between say between 1 and 3. Okay. Well, then maybe to make this example more concrete, maybe we set lambda equal to 2. Okay. Okay. See that? Okay. Then what this says up here is that the chance that x is between those two numbers, 1 and 3, maybe 1 and 3, I don't really know where they are, but something like that, is just the area beneath the curve. Right? You should have seen this in a first semester statistics course when you talked about normal random variables. At least when you have continuous variables, the idea is that the probability is the area. The probability is the area beneath the curve. Right? The probability is the area. Okay. All right. So this will be the integral from 1 to 3 of that density function, right? Between 1 and 3, the density function is just this stuff, okay? So it's 2e to the negative 2x dx, okay? And we've actually already solved this, remember, from the other page. It turns out to be 0.135335, okay?